So what I'm going to do, so that you can see a little bit clearer, is I'm going to try again to trick it a little bit here to think that my screen is bigger. Okay, that'll work. Okay. So we're going to talk about the rationale of using R. And let's see, on Monday, Tuesday, and Wednesday, you saw a little bit of MATLAB code, I gather. And what else? Next week will be Python. So somebody's going to be, oh my gosh, what are these guys thinking about? Who's going to spend the time to learn R, Python, MATLAB? And some people are going to show Unix commands. You know, well, so why is it like this, really? Why is, you know, what's all this? Yeah.
Complex processing needs specialized tools.
Okay, complex processes need specialized tools, but why can't these guys, you know, you and I and Joe Schmo, why can't we get in the same room? Because, you know, I mean, programming, you know, you guys are too young to remember, but when I was in college, we had the punch cards, you know, and 2 punch cards, you know, it's machine language. You code the same sentence and I code it, it's the same punch card. I can plug it in your machine, you plug it in my machine. You know, there were standards. Now we're coding, you know, well, it is an incredible feat of human ingenuity, the fact that we have all these alternative ways of thinking about processes, okay? So you don't have to become experts in any of these, and believe me, I'm certainly not, but you have to have a little bit of exposure. You know, I've done coding, you know, machine language, yeah, I had a class, you know, it's crazy, nobody codes in machine language. But the next to machine language is programming in C and C++. You know, it's as far down to the kernel of the operating system as possible. And, you know, I've written hundreds, thousands of lines of code in C, not in the past 2 decades. Why? Well, because speed that it gives you and power to get the native system resources, we don't need it anymore. You know, high-level programming languages, you know, that's what you do. A single sentence in C may take, you know, 10 to 20 to 30 lines of code. So people like to code, and people always simplify, right? Then came object-oriented programming back in the mid-90s. You know, Java, you know, and all the other languages after Java, after the mid-1990s, everything is kind of object-oriented, you know. So we've got these objects. So what are objects? Because this term is going to come up, right? I know the computer scientists, the engineers, you guys know what objects are. For the rest of you, an object is an instance of a container that stores members. And members could be data elements, structures, descriptors, metadata, functions. So you can think about, you know, there's many examples of objects, but an object itself comes up with functionalities, just not a data structure, the way the pure language C is, right? It's not just a data storage container. It's a container that has members that are not necessarily data. They could be references, they could be functions, they could be methods, you know, a variety of things. So, you know, it is interesting. So we're going to talk about the rationale of why do we use R as opposed to MATLAB. And, you know, typically you would get to associate with a language that's your primary language. For me, you know, I started with C, then I went into Java. You know, I've got hundreds of apps in Java. I personally think Java was the most incredible language, but lately it's coming out of fashion simply because the front ends, the GUIs, the graphical user interfaces, have been suppressed by most of the app developers and the browser technologies, mostly because of hype. But Java is a beautiful language, and if you want to learn a new language, a new lower level language, Java is the way to go, I believe. But we're going to be using R. We're going to see some demonstrations. We're going to look at how to install R and how to use its graphical user interface called RStudio. We're going to show some R commands, introduce data stratification and subsetting, some simple things about, you know, generating cohorts, right? We've got a huge collection like the ADNI, like the PPMI that I mentioned earlier, and you want to separate the individuals into clusters or groups by their clinical phenotypes. So how to do these types of things we're going to talk about generically, you see. And then we're going to talk about some of the mathematical operands, functions, how you compute various statistics. Matrices, we're going to downplay a little bit matrices, because not all of us are necessarily, and you don't have to be a math whiz, I guess, to deal with some of these matrix operations. And then we're going to talk about visualization in R, as opposed to the web-based thing that I showed you earlier. And then a little bit about model fitting. So let's start off with why use R. Well, it's one of the largest open source communities. 100,000 and over developers. 20,000 R packages, you guys. Nothing out there gets close to what R has. In terms of, I'm talking about statistical computing. There is more Fortran libraries out there, and more C libraries, and certainly more Java scientific libraries. But when it comes down to statistical computing, the most innovative statistical computing things are always implemented in R and validated in R first. In fact, you know, a bold statement would be, if it's not in the R archive, it's not fully validated. Everything else, you know, you look at SAS, Stata, SPSS. These are toy languages, you know. These mostly work with, you know, spreadsheets on the order of, you know, a few hundred rows by maybe a few thousand columns or something like this. You know, important problems, but not, you know, on a, this is as far high up as it gets. But sometimes to get to the top, you gotta do a little bit of work on the bottom, if you know what I mean. So, you know, there's pros and cons. Look them up. Obviously, the learning curve is a bit steeper for R. Okay, and for some of these other languages, you know, you put in front of an in front of a SAS terminal, you know, click here, load the data, put it in, you know, manipulate the columns, click and paste. You know, these are mostly things that are standard. There is licensing issues that come up with some of these proprietary products, and you got to be very concerned with this because your license will expire. My licenses certainly have in the past when I used to use them. So there is pros and cons. Now let me show you a little bit about when it comes down to comparing most of the things. Okay, so here's your Python. Julia is a recent language for, again, big statistical computing data. R, the interactive data language, IDL, is popular as well. MATLAB, Scalar, C, and Fortran. So I've created this table that kind of tries to provide you a little bit of intuition about what the different platforms offer you. So whether or not it's open source, and again, I'm a huge believer of open science, which includes open source and fair data sharing and all that business. But this is important for me. Again, if you coded something and you patented the algorithm, you know, I can't integrate your algorithm with anything that I'm doing because I share stuff openly, and your license is viral. It infects my stuff, so it goes out. It's not in my world. It's a different universe. So if you want to stay with proprietary stuff, then that's a different level. You know, during those 3 days that you're with me, we're in the open science community, and this is very important for us. Speed is important for everybody, right? I mean, I'll show you. We've got thousands of subjects going through hundreds of steps. How do you do that? You know, time becomes an issue, believe it or not, and I'll show you some examples. Well, okay, so look at R here. So R is, these are extrapolations, okay? It depends, well, exactly what test did you run, what benchmark data did you use. You know, there's quite a bit of variability when it comes down to these scores, but higher typically means better. So the speed of R is very marginal. It's at the bottom of the pack. If you want speed, if you're a high octane guy, you know, you want to go, you know, fast, R is not where you want to go. Well, with some exceptions, because R, you know, it actually allows you to write your code in a very low-level language like C and just use R to invoke it. So all the calculations happen natively down in C, and that's how you can export it. But I'm talking about using standard R, standard libraries, a lot of interpretation. You can think about R. It's not an interpreted language, but you can think about it as an interpreted scripting language. Okay? And because it's interpreted, it's not compiled, it's not very efficient, right? But again, if you want efficiency, you can hard code your highly compute intensive kernel in C and just use R to code that object, and then it's going to run as fast as you coded the object in C. R has nothing to do with the actual execution. So what I'm saying is that take this with a grain of salt. The slowest of all is R. MATLAB, you know, so Scala is the very optimized. C is absolutely, you know, Julia and C are, you know, the top performance if you want to look at speed. Computational time is obviously inversely related, right? Speed and time, you guys. So here for the compute time, you want the fastest, and you see one task took Julia less than a second. You know, R may take 700. That's 12 minutes or so. You know, a huge order of magnitude slower, but that's what it is. But then look at the library extent, you guys. The library extent tells you how much functionality is available for you to tap on. Okay? And look at R. 100. This is the top stuff. C, you can obviously do everything in C. Fortran, you know, I mean, who codes in Fortran any longer? There's a lot of good Fortran code. Even some of the R packages might tap into existent Fortran code, but you can do a lot of things. And then look at MATLAB. You can Scala, Python. You know, there is a variety of extent, I guess, in terms of the libraries that you have available to you. Ease of entry kind of tells you how quickly you can step in that environment and do something meaningful. So, you know, there is a bit of investment that you have to do in some of these things. Costs associated. All the proprietary languages would have cost. Now, cost is not always money, or it's not always licensing. It's the burden that you incur by kind of committing to, because, you know, we're going to be going through right now and installing it. Well, that's a commitment. You got to go ahead and update your R in 2 months. Well, that's a commitment. So time and money, you know the proverb, right? Time is money, money is time, you know, whatever. So cost is not just monetary cost, but cost of ownership, if you know what I mean. So, and R is a very, very lightweight thing. Very lightweight, very elegantly structured. And interoperability, very highly interoperable. Some of the other things that are proprietary, well, you can install other things. Again, you don't need that, but you see very soon how much advantage you have by running stuff in RStudio. Okay, so let's go ahead, and if you haven't done this, just right-click here, install this, install RStudio. I think Eric just installed it this morning. Okay, that's fine. So here you're going to be done. So RStudio makes their money from essentially licensing either system-wide versions for big services, for big companies, or supporting these RShiny servers that allow you to write code. And you know, it's interesting. I wasn't planning on showing that, but if you want to know, well, I've written this R code, and I want to make it available for other people. How do I do that? Well, you provide it as an RShiny object, which gives you a URL address for your specific app. And some cool things arise. So these people at our studio, they allow you to run our services on your own hardware, so that people don't go to shiny.io, but they go to myorganization.org, and then you provide the service, not them. Anyways, so products are studio, and this is the Server Pro, which is very expensive, by the way, but we're not in that business. So let me see. Again, it's going to be the same experience. The 3 different platforms, you're going to be downloading the corresponding binaries. Installing will take, whatever, 30 seconds to 60 seconds. So why don't we just focus on the folks that do not have our studio yet? The rest of you guys, who doesn't have our studio yet? You don't? You have? Okay. You don't? Okay. You started already? Okay. Anybody else in the back? You guys have our studio? Okay, very well. Oh my goodness. Is it a network issue or?
Yeah, it's a
Okay. Okay, so I'm going to stop this then to release a little bit of network pressure. So for the folks that have it, go ahead, you guys, and start looking at down the notes a little bit about the organization of our studio. Maybe grab some of the code. I will also start. Eric, did you install our studio or did you just download it here?
Just download it.
So is that going to download? Okay, so Eric is going to show you now how.
Yeah.
Wait.
Okay, on the Mac it's really easy. You download the .dmg file. Once you open it, you see a link to applications folder. Go ahead and open that. And this is your RStudio. Your RStudio, the .dmg file opens up like a disk. All you need to do is click on this. Left click, hold the left button down, drag into the applications folder until you see the plus sign, release.
So double click doesn't work?
The Mac, they don't really install the programs that are standalone. So it's copied. I just double click on this now.
Okay. Okay. Great.
It must be the search of downloads.
Okay, but it's not projecting in that.
It's not detecting the receivers. There's maybe too many wireless connections and probably just drop. Couldn't detect the receiver.
Okay. So the folks in the back, the monitors are not working. Can you guys see that or is it too far? Well, Okay, well, if you guys need to see that and you can't, we can either move some of the tables or there is a few extra seats here, I suppose. Now that, so let me see. You're still going on, right? Okay. Oh, finished. Do you have this? Do you have the RStudio now? Do I have? Okay, so everybody has RStudio now. Yep. Open. Okay, so let's see. I'm going to maximize it, and under, let me see, was it view? Okay, zoom in. Okay, that's probably a little bit better. I can maybe zoom in a little bit more. Right, I did, but I won't, right. All right, so there is, let me just see here, view. Okay, that's what I want. Okay, so you guys, let's just pay attention a little bit. Some of this is described in the notes over here. You know, about the different panels, I guess, and whatnot. So I'll just tell you on this instance. So I'm running an instance of RStudio. It's got 4 basic blocks. So on a Mac, on a PC, the options are right up here on the top bar. But you basically have, you know, file, imports, exports, you know, imports of data, saving and whatnot, editing tools, code. View is where I zoomed in a little bit, and there is quite a bit of customization. Some people, for example, like to have a black background or something. You can highly customize the experience of the RStudio, depending upon, you know, what you like. You can change the fonts, etc., etc. So play with this later. But roughly speaking, sometimes your R session may get in some kind of an infinite loop or something. You can terminate R, restart R directly from RStudio. This comes in handy once in a while. Tools. Now here, remember what I did early on. Let's see if I still have it in my buffer. Okay, I need that, and then I need some of the other things that I did to get this to replicate. So let's go ahead and grab this with the mouse, copy, paste it in here. Now, so I have the source code here. Now look, I require simply means if you have these packages, load them in my instance, because you're running an instance of the R in virtual machine, okay? And now you can run things 2 ways. The first one, oh my gosh, it's coming out of, let's see. The first way to run things is you highlight the line that you want to run, and you see what I did here is I simply clicked on this button to add up a new R script. You guys? See, I can add up tabs here with different source code. So you should give these things names and typically save them. I can save, let's save the first one because let's see, file, save as, and I like to save things in my desktop. Where is the desktop? Oh, desktop is this one, right? Okay. And I'm going to code test1.r. Remember, every script that you save in R needs to have the extension of .r so that it's properly interpreted. Later, we're going to talk about R markdown files, which are really cool, and many of you can make a great use of them. The examples that I provide in the book are R markdown code. but it's equivalent to R. So I'm going to call this test1.r, and now you see how we changed this unknown name here in the tab to R, to test1.r. And again, if I highlight this line and just click run, it tells me it runs it. This is the console. This is where the R run script. This is my file that I'm playing with. And on the top right corner, I have environmental variables, some of the history that I've run, etc. Because sometimes you may want to push this history to console or to source if you want to redo some of these things. You see? Okay. Now it tells me that this package ggplot is not available. So no such package. So here's the critical part. The R environment that we loaded comes very lightweight, and that's why it's so quick to download. It only comes with some rudimentary functions. Most of the advanced functions, they're coded independently as R packages, and for whatever library you need to download the library and then load it into the R session to be able to use the functionality. So let's demonstrate how this happens. If you go to packages, see, these are the packages that currently came with the R installation. There is about 30 of them. Notice how some of them are toggled on and some of them are not. The ones that are not toggled on are available to you, but they're not currently loaded in your R session because they're not critical packages, and every time they're loaded into R, they occupy some resources that can be used for other things. So you don't load everything unless you need it. It's a very important lesson. Okay? So this package, ggplot2, I'm going to copy the name, and I'm going to go into Tools and Install Packages to go ahead and download the ggplot package locally. And I'm going to paste it in here. And it's going to ask you, well, where do you want to download it from? And where do you want to put it? Let's just keep the defaults for now. And I'm going to click install. Probably most of you will have to do that. You guys, is everybody here with me? So again, Tools, Install, give the name of the package you want to install, click Install. And you see what happens here in the R shell. Okay, it's working on installing the package. So this works a little bit different than on a PC. So what it's doing right now is it's trying to retrieve I think it's downloading right now the ggplot package from the internet and putting the binaries locally, but it doesn't make them automatically available in my current shell until I load them into the my R environment. So we got to give it a minute here. I have to do the very same thing for reshape. Yeah.
What's the difference between require and library?
It's the same thing. Require and library is the same thing. It just loads them in. And in fact, if you right up here, see, I tried to look for ggplot. It's not available. So if you toggle boot, for example, it uses library by default. I tend to require, it's the same command. I think one offers more options or something like that. It just brings it into the environment. Again, it reduces the amount of available resources. So if you don't use something, always detach it so that it releases some of the requirements. So all right, we're going to give it a minute. You're probably facing the same thing. It's
Try to switch to a different wireless network.
Yeah, so that may be a persistent problem as you go forward because, I mean, there is 30 of us accessing, you know, a 10 megabyte, which is very, very small thing, times 30. Now you're talking serious data going through wireless.
So I recommend you swap to the Cape Guest wireless network to do the install.
But if all of us swap to that network, we're going to have the same problem. So, I don't know, evenly distribute, I guess. So, notice before we press on, sometimes when you install packages, they have dependencies. In other words, the functionality in one package requires something else. So this package, ggplot, requires oh no, we don't want to install from source. I just want the binary, so probably no in this case. You can install from the raw source file, or you can just download the binaries which are already pre-built for your specific operating system. It's always easier to just download the pre-built libraries. But I was going to point out that you see all these things? It's downloading different dependencies that it needs. So GG table, for example, so variety of, so it's going to, again, every package when it's released through the CRAN library declares specific dependencies. They're all installed here. So now you guys, if I do the same search here, so again, the panels, here is the source code that you save on local hard disk. Here is your environmental variables and history of things that you ran, you guys. You can always click on this and put it into the source or put it into the console. So the history is important. The environment shows you what variables. I don't have anything in my environment yet. I haven't defined anything. But soon I'm going to define a data object that stores these 3 columns, remember, for the publications. And I'm going to have one object here. And then, so, source code. This is the execution, which is the pure R that you can run. Here is environment and history. And here is a whole bunch of things, including plots that we're going to be generating, some things about files, the packages that you currently have access to. Remember, a second ago I searched for ggplot and it says not inappropriate found. If I search for ggplot now, it should tell me that ggplot is available. It's not loaded in R, so I can either type in require and push it, run it, or I can just toggle this thing off, which does the same thing. It makes this package available, and it's all of its members and functionality available for use. Is everybody here with me? No. So 2 ways to load the package into the R instance for use. So I typically use that version. You can also use, you can also just run the require. It does the same thing. So let's do the same thing with the reshape now. Let's try to see if reshape is available here. Okay, reshape was available. Let's see where it is. Reshape. Okay, it's already loaded in. So now what I'm going to do, you guys, is I'm going to grab the data, just like we had before. And now my environment, all of a sudden, after this command finishes, is going to have, boom, 2 objects are available for me here, okay? One is the actual raw data, and I can view that. So for example, I can type, oops. View. So view, look what happens now. And if I start typing, our studio is very smart. If you start typing a few keywords of an object name, it's going to suggest what it might be. So, for example, I have capital D, data, and it tells me what I can choose from, right? Does everybody see the list? So, of course, I want to view the data that I just downloaded. And it's going to show it to me as a spreadsheet in the top left canvas here, right? So let me kill this. It doesn't have anything. So I know that here's my data. If anybody wants to see what was the data behind the graph that we saw a second ago, it's the 20 years, actually 21 years. 95 to 2005 is 21 years. Let's make sure we get the years right. And R, I was in grad school when R came to be as a language. It evolved from something that was called, the statisticians were developing something called the S language for statistics. So R, two guys, their first name started with R, and the hypothesis is that R comes near S, anyways. It became known as an R, and it's the open source version of the former S language. So that's how you can view data in a spreadsheet format. Now, sometimes you just want to make sure that what you intended to read is correct. So you're not going to be copy-pasting here, or this is not Excel spreadsheets. This is just to show you, roughly speaking, the column names, and roughly speaking, the type of data that you have, right? And you can scroll if you want. Anyways, so back to the little code here. The next thing is this melting. Oh yeah, so let's go ahead and do this. So I'm going to run this command line. Again, highlight the command line and press the run key, the run button here to send it from the source file onto the canvas and run it. You can also, with the mouse, copy paste it. So let me demonstrate this. Control C, click on the canvas, Control V, paste it in, hit enter, and then let's just view this new data frame. Notice how, so here is the original, you guys. It came in the white format. For every year, I have one row of 3 records. When I converted from this white format to the long format, it looks like this. I have a year, and then I have a name and value pair. The name and value pair is for which language or which environment I'm talking about, and how many citations were there. So now, remember, we went from a matrix that's 4 by 21, which is 84, right? 84 things, into a matrix that is 21 times 3, which is 63 rows, should be. Oops, hold on. 45. Oh, okay, I didn't scroll down all the way. 63, okay. Just to make sure the math is right here. And so it's the same data, it's just slightly morphed, okay? Is everybody here with me? So, all right, so next I'm going to go down to the actual plotting, and now I'm going to just click on the run command, and now look, I'm now in a pack. I'm going to get to some of these guys later. I'm in the packages tab on the bottom right corner. If I run this plotting routine, it's going to switch me from the packages to the plotting, and now here's my graph that we just generated. I typically click on zoom, and zoom you can maximize, and then right click to copy it as an image, or save it, or I suppose. Oh my gosh. Okay, so that's different on a PC. Okay, it goes probably in some kind of a download directory. Anyways, look, I can copy it, and if you have let's see. Let me just, I meant to open Word. I just need a place to paste this image just to show you that it's in my mouse buffer, and I can include it in a publication or something like this. Okay, blank document. Oh, create. Okay. Sorry, this is a bit different, the interface. Okay, so I have in my mouse buffer, so I'm going to do control paste. So here is the image, right? You guys, you can save it, whatever, PowerPoint it, whatever you want to do. Okay, so let me close Word to release resources again. Don't save, and close Excel. Okay, so this is my zoomed in version of the dynamically generated image. Was everybody able to generate this image? I mean, you know, the syntax is not as important right now of the specifics of how this image is generated. The important thing is that there was data living in the cloud. We downloaded the data. There was some packaging, some data manipulation, data wrangling. We went from wide to long format, and then there was a plotting. That's the important thing now. Okay? And then kind of to get oriented in this syntax here, I typically, if you don't need something, get rid of it. That's, you know. So this file I can save. Yeah. So this should be on my, replace the original one. So let me see if I can see where is this file now. Oh, I see. You open a new thing for me, right? I beg your pardon. I didn't see. Okay. So I'm going to drag it in. Okay. Is that how it works?
Yes, that's great.
Okay. All right. So I'm going to be saving. I have a folder here. Okay. All right. So let's see. So we've got the layout. Okay, some notes about syntaxing. The assignment operator in R is less than followed by the minus sign. So this is a right to left assignment operator. You can use equals as well, but equals sometimes has a different meaning, that plug in that value that's on the right side into the name that's on the left. So try to get used to this operator, although sometimes you see we use them interchangeably. So here's, for example, the assignment of x is going to have the value of 2. When you need help, you can either type help on a topic or just use the question mark. So here is my RStudio. I can do okay, all right, so let's go ahead and close it, but I'm going to open it appropriately now. Open it from the desktop over here. So it completely from where in RStudio kind of monitors these files. It says you don't know what you're doing. It's right. Okay, so yeah, I was going to do a help. So you can do help. And you see how it always, look at these pop-outs. These are very helpful things when you don't know the exact syntax of a method or something. RStudio provides these very helpful. So for example, if you know which package is the topic in, you can provide it here. In general, let's say I'm looking for linear. Suppose I just type linear. Okay. The string completion. Okay, so why don't it says I don't have anything on linear in this exact phrase. So I'm going to do a question mark, linear, and you'll see that I'm going to get exactly the same outcome. It's going to say nothing known. But if I put a double question mark, it says, so I'm copy pasting all the time. You guys have to get used to copy pasting just to get quicker responses. Now here in the help, it's going to tell me everything that has to do with linear. So look, I was actually going after the stats package linear model, but I didn't want to type LM for linear model because that's presuming I know how to call a linear model. I didn't. So right here, you see, it kind of tells you, so I can type in the search query here, linear model. Linear model, and then it narrows the search, right? There is much fewer things, and the thing that I'm looking for is this specific thing. And by the way, look at the forward and backwards arrows. You can always go back to where you were in the help, in the plots, in everything that you've done. You can kind of go back. It's almost like a browser with its history for going back and forth. These are very useful things to remember. So I just wanted to get some help on the linear model. This is the simple function that I wanted to get help on. So it tells you it's part of the stats package, which by the way is always loaded by default, because after all, R is a statistical computing package. So the stats package that comes with all the basic statistics comes preloaded. And it tells you a little bit about the package and how to use it. For example, you put in a formula, you provide a data set, and various other optional arguments. All of the arguments are defined, and then what this method returns to you is called the result of the call, which follows after the details. It says the value returns an object of certain class, and it ends with an example. So this example everybody should be able to run. So here's an example where we have two groups, and by the way, you guys, if you bring the mouse over the center, you can maximize any one of these panels. You have to be careful with this because it's going to shift your code in the top left panel a little bit, so you got to be careful navigating. But sometimes if you want to read more of that, you can kind of zoom in a little bit on the window. So what's happening here is this has two column vectors. C means a column vector with these how many values? I don't know how many values, but let me go ahead and run this. I can copy it with my mouse and put it in my console over here. Hit enter, and then under the plots, these are some of the plots that were generated from these data. Now, mind you, it computed over here a generalized linear model for these data. So, and now I said, well, how many values are here? This control and the treatment, I can actually do print the length, just type length. And you see, as soon as you type 3 letters, it suggests for you the most appropriate things that you may be working on. If you press tab, if it has highlighted the right command, I can press tab to complete it. And then inside I can just, the name of this variable was what? It was called CTL for control. 10 observations, okay? I'm sure the treatment, the second variable, also was of size 10. Oh, and by the way, the up and down keys on your keyboard run the previous commands, okay? So you see how I type this? I just pressed, and if I go farther back in time, see, it tells me what I typed in the past. Just the up and down keys, you guys, so that you save on typing. Okay, so I want the length of the treatment. Should be 10 as well. Okay. So again, here is the canvas with our source code. We can run some of this. Here is the canvas with the environment or the history of what we've ran. And here is the help, packages, and plots that we've generated. Oh, look, you're going to see this many a times, and it is difficult, okay? Look what happens. I reduce the margin of my plotting window, and it says figure margin too large. The figure was too large to be plotted in this small canvas. So if you see this, there is two solutions. The first silly solution kind of is to zoom in that, and then the figure is going to render. Okay? But the better solution is to redirect the plotting to an external file where you control the resolution, the size of the image, and everything else. We'll talk about that. I just want you to know that you have too much stuff packed into your desk environment, and sometimes you will get that problem that I just showed here. Okay. So, and I'm not sure if Zoom is going to work. Okay, Zoom works. Okay, that's fine. All right, so any questions about the organization of the RStudio graphical user interface? Yeah.
I can't seem to get the GG1.
Okay, let's have a look. Did you download the package? Okay, so
It's what it says here. I can get the DM, but
okay, can you click on packages? I want to show you. Find GG plot. Yeah, click it off. What's it say? Can you try to run this require GG block? Just highlight the first line. Highlight the first line and click go. So I don't know what happened. Now it's started off, so it's working now. Strange. I'm not sure why. Because you see, the library and the require should work the same way, but in your case, it didn't.
what I did was I did show us like the other one, which is kind of this, and then
Yeah.
I did that. But when I run the last command,
The actual plot. Oh, can you run it now? Yeah. Oh, yeah. Okay, so that's an important point. He reminds me that sometimes you guys, if you run a plotting here and you click run, it will not render it in the plotting window. If you want it rendered in the plotting window, you have to copy and paste it here, because this is the window that puts stuff here. This is just a source code. So let me just demonstrate this. If I click run, you see nothing gets plotted here, because it actually gets rendered see invalid graphic state. If the file that I'm editing now was an R markdown, RMD file, it would have plotted it right up here in the source code itself. We're going to show you examples of this. So to get this to plot, I need to do Control-C here, paste it in here, and hit enter, and then oh my gosh. Oh, okay. I have to reset the graphics. Hold on one second. Hold on one second. All right, so I had, remember how I ran one example that generated the linear model plots? It changed the layout, so I had to refresh my plots canvas by clearing everything. And you see these arrows are not disabled because I don't have a previous plot and a following plot. So that's why, again, that's a good point. So does it make sense why running it here does not generate the plot in the... I'm going to go back to the notes. So here's another example. Let's just look at this. This is, you know, kind of simple terms. Another example showing this melting of data set from long to wide. But this time, you're literally generating a data set on the fly. So you see, remember before we used the command called read CSV to read the data from a local file or a cloud service. In this case, we're going to be using read table, and the table is actually given as a text file that starts over here and ends right after the quote. So it does have a header, and by the way, these booleans, there is many arguments of functions that are boolean in nature. They're either true or false. The capital true and capital false are reserved commands in R. You can abbreviate them to capital T and capital F if you want. So we're essentially generating a text. This is free text between the quotes. This is the start, and that's the end of the free text. The actual text is in between what I'm highlighting here. 5 subjects, 5 rows, and then 5 columns. Case ID, the first one, gender, age, condition 1 and condition 2. And then what you want to do is, you see this function factor, it essentially indicates that the case ID is going to be considered a factor variable. And mind you, this is very R-specific notation. When you have an object called raw data underscore wide to indicate that the data is in the wide format, 1 row per case, including all the features, all the time points, all the characteristics on the same line, then so you have this object called raw data wide. If you put a $sign and then a column name like case ID, it simply refers to the column, the first column. All of its values are going to be considered to be factored. You could have done factor for gender because gender is obviously a factor variable. Well, actually, let's take a step back. Does everybody understand the types of variables? Quantitative, qualitative, factor variables, discrete, continuous, categorical. Is everybody comfortable with that? With these descriptions? Any questions about, so factors typically refer to categorical variables that may or may not be ordinal. They may or may not be comparable in terms of comparison bigger than or equal to. So we are just constructing a new variable called subject. And you see, we are going to add it to the old object called raw data wide. We're going to call subject to be a factor representation of the case ID. And now if you go ahead and print, just print the name of the raw data variable, it's gonna print out the very same 5 columns that we had before, plus the extra column that we just generated, which in this case equals the case ID, but it could have been something different. Now, again, the reshape2 package has the melt function, and that's a very interesting function. It allows you a lot of flexibility when you want to reformat or restructure data. In this case, we are simply going to be using the case ID and the gender as variables that are not long expand. So these are going to be the ID variables, and everything else, which includes Okay, case ID and gender we're going to preserve. So case ID and gender. The other variables, age, condition 1, condition 2, and subject, they're going to be expanded from the wide format down in the long format. So you see, again, subject 1 is a male, and then they are going to have how many new rows are we going to have for subject 1? Well, we're going to have a row for each of these variables that we did not ID on. So 4 rows are going to have the labels case ID is 1 and gender is male. So here is the first one, namely storing the variable age. Here is the second one, storing the condition 1 for subject 1. Here is the third one, storing the condition 2 for subject 1. And the last one is right up here, storing the subject ID. So again, this is a reorganization of the data. And here is a little bit more of a description if anybody wants to go deeper into the melting package. So the ID variables are the variables to keep but not split apart on. In our case, gender and case ID. All the other variables, including age, condition 1 and condition 2, are going to be split on. And then you can simply print this long variable that you call. And now look at the assignment again. The label data underscore long is going to be the name of the new expanded data format variable. And you print it and it kind of looks like this. So you don't change the data values, you don't change the amount of data, you change the configuration of the data. Now there is a package called well, the article is called Tidy Data, but the package is called, there are several packages that do tidying of data. So you may want to read this article if you're interested in getting a little bit more about data manipulation. So let's go over some of the simple things, like creating a new column vector, which we already saw when we talked about the linear model. C stands for column vectors. Data in R is stored as columns always, and the first index of the column is always 1, not 0 as it is in the C language, for example. So here is where you construct a new column A that has these 10 or so values, and type in the name of a variable always reports its content. So be very careful printing stuff, because sometimes these data objects are very large, and if you print it, first of all, it may take a while to go through the thousands of lines of information that these structures may include, and second of all, if you have too many columns, they're not going to print right. So typically people don't print the values of a data set. And you can use, there is lists, there is repeats, you can recursively label things, standard things, you can construct sequences from 1 to 10, for example, using the seq command. You can specify the step of the sequence. This is useful if you want to construct a variable that gives you the time points at which certain observations are labeled. If you only have the recorded measurements, but you don't have the time points at which they are recorded, you can use sequence or repeat or something to generate time points, and then you plot time versus observation using the plot command. We're going to have some of these examples. The length function we already saw. It tells you how long is a univariate single column vector. If you have a matrix that's two-dimensional, you need to use the dim for dimensions to print its size, right? So linear objects have length. Planar objects have areas, right? Which corresponds to the dim for the dimensions. Objects that are three-dimensional are also going to have dimensions, right? X size, Y size, and Z size. So these are common things that commonly are used throughout. You can construct sequences repeat various measures. In fMRI, for example, you typically repeat the same time points, but the specific paradigm that's applied at each time point may have to vary. So data frames. So what are data frames? These are objects that are created either from matrices or from other, they're called tensors. A higher order matrix is a tensor. Think about a three-dimensional lattice where your indexing for the intensity is indexed by the x location, y location, and z location. This is a tensor, and you can make a data frame out of it. The data frame is a little bit more than just the values that are included as intensities. For example, a data frame can contain row names, plane indices, and cross-sectional. You know, if you go from sagittal to coronal to axial, it may have some additional metadata. So a data frame is the actual data plus some metadata describing the data. That's the way to think about data frames. So here's an example where we create a silly data frame that has some numerical values in the first column. In the second column, you simply have 4 characters. There are 4 strings actually, but each string is a single character string. And the last column is just the values 10 and 11. Now, when you do this, a data frame is always rectangular. Look, the first column, it has length of 4, right? Because I have 1 to 4 in increments of 1. It goes 1, 2, 3, 4. So the first column has 4 elements. The second column also has 4 elements, but they're categorical. And the third column has only 2 elements. When you have 2 elements like this, they need to be, R allows you to do that, but they need to be, the number of the other rows need to be divisible by that number so that you can stack them together. So for instance, let me show you how this command is going to fail if I put a third value in the last column. So right up here, if I try this, this is going to work nice, but if I add up an extra number here, so it's going to complain because I have 4, 4, 4, 4, 4, 4, but the last one has only 3 elements, and there is a gap here in the corner. Is everybody here with me? That's why it's going to complain. If I only put 1 element, it's going to replicate it. It is going to replicate it 4 times. So right up here, if I put in 12, it's going to replicate, oops. And now that's interesting. So what happened now is I have opened a bracket, something happens, but the bracket is never closed. When I press enter, R understands I haven't finished my command line, and it says you gotta keep adding. And the thing to add right now is a closing brace, and that's gonna be okay. The number 12 is gonna be repeated 12 times because 4 is divisible by 1, the size of this object. Right? I mean, this is not very interesting, but to kind of give you a little bit about the syntax that R uses, let's keep on. This is important now. Arrays, because all the neuroimaging data is given in arrays, right? And they're complete arrays. You don't have arrays where there is a missing value here. The machine will generate complete data. It may be wrong, but it will be a value here. So, so you have the row indices, okay? You see the first index, 1, 2, 3, 4, 5, kind of shows you the row that you're in. And then the column indices are the second index, 2, 3, 4. And then the plane, you know, the section, kind of gives you the page or the depth or the plane index. So that's the last index, second plane, third plane, etc. If you have a 4-dimensional object like an fMRI time series, you want to have an extra element here that's going to be indexing the time point. So you imagine this 3-dimensional matrix and one time dimension, time 0, time 1, time 2, etc. Right? So it is very important that to understand that these indices are not swappable. If you swap 2 indices, you're jumping around in this matrix, right? So look at the element 1, 1, 2 and the element 1, 2, 1. They're at completely different locations, right? So in the C programming language, the first index is always the fastest varying index, and the last index is always the slowest varying index. When you store matrix data in memory, it's always stored linearly. So think about unfolding this stack of planes, each plane representing rows. The way you unwind it is you write the first row, and then the second row gets pasted right up here. The third row is after that. The fourth row is after that, etc. And once you exhaust the first plane, you go to the second plane, get its first row, paste it in here. Second row goes after that, and you string them all together. You're going to have exactly as many indices, exactly as many entries as the product of the dimensions. In this case, 1, 2, 3, 4 times 1, 2, 3, 4, 5. 3 times 4 is, no, 4 times 5 is 20, times 3, 60 elements. So if you unstring that matrix, it becomes a 1 by 60 array. Does everybody get that? And how you recut that 60, this array of 60 elements, if you cut it into fragments of 4 versus fragments of 5, you know, you're going to get a different rendering of the same volume. So you got to be careful a little bit with these things. But this is the typical indexing. If you, in R, if you skip an array, you're referring to the entire column here. So for example, the object that's referenced by 2 blank 1 is going to have the second row, the first plane, you guys, the first plane, because these other planes are plane 2 and plane 3, right? So I'm looking at the first plane, second row, any column. So I'm referring to these 4 observations, these 4 intensities. Is everybody here with me? Now, if I had left blank here in the beginning, this would simply refer to the entire first plane, any row, any column. Right? Okay, so this is a very shorthand notation in R to traverse and aggregate multiple things. Now, they need to be cardinal projections. You can't say this and this and this. You got to explicitly list the indices, but this is a shorthand notation for the things that are kind of vertical. All right, so here are some examples and whatnot. Reading data, we've already seen the reading data command. Oh, this is important. Here we've actually printed some statistics. If you do summary of any object, the object could be the result of a linear model, the object could be an array. Summary of anything kind of gives you a succinct representation of what's in it. So in this specific case, we've loaded a data set from the cloud. Let me copy paste it into my RStudio. Okay. Let me copy paste it. Oops. Downloading the data. Oh, and by the way, sharp, the sharp over here, the sharp over here indicates everything after a sharp is considered a comment. And that's why in the notes it's gray color or something like this. So if you want to say what it, so okay, back to here now. It downloaded the data and it told me that this specific data set has a whole bunch of variables. Tumor size is one of these variables that it has, and it reports for you some simple statistics: the minimum, the first quartile, the median, mean, third quartile, and maximum. Now, Does everybody know what the quartiles are? The first quartile is the value that separates the data into the smallest 25th percentile and the largest 75th percentile. The second quartile is the value that has half the data bigger than it and half the data smaller than it. The second quartile is also known as the median. The third quartile is the 75th percentile, meaning only the largest 25% of the largest observations are to the right of it, and the remaining 75% are smaller than that value. So the quartiles, which you have three, Q1 is the first quartile, the median is the second quartile, and the third quartile is Q3. They tell you something about the distribution of the data. In fact, the difference between the third quartile and the first quartile is a measure of dispersion. It has the central 50th percentile of the data, and if this is wide, it means that the data is highly varied. If the interquartile range is what it's called, is tight, your data is most likely very tight, less noisy. Also, you can do the same thing with the minimum and the maximum. The difference between minimum and the maximum is another measure of dispersion or variability. And if you have missing values, it would report just below the maximum, it would report NAs, NA for not available, NAs, and it's going to tell you how many missing observations are in that feature, in that variable. Remember, you can also use the view command here. And another important command is just head of this what is it called? Data. .csv. If you just do head of an object, if the object is data, it reports by default the first 6 rows of your data. You can also use tail and report the bottom 6 rows of your data. This is sometimes useful if you want to troubleshoot, just to make sure that you got all the subjects or something like this, or the data. You can also use column names if you're only interested in the names of the features. Oops. Data, CSV. What are my column names? These are the features that are available in this data set, right? And you can use, remember the view also, you can load it as a spreadsheet if you want to. Okay, just a few closing remarks here. You know what, for now, let's not worry about too many of the technical details, but I want to tell you that in R there is a very clever syntax that allows you to subset a data or generate cohorts that meet certain criteria. For example, you can say, pull out of my data object all things that are in the following columns. I can say, pull out all the data that has between these two values. You can pull out certain columns, you can pull out the first, the fourth, and the second column only. You can manipulate the data very effectively with single command lines, just to stratify and extract the data that you're interested in. For example, if one of the columns has the gender, the sex of an individual, and you're only interested in the females, you can specify here that you're interested in the gender equals to male or female, and it's only going to pull out these values. Okay, so there's a lot more things that we can look at. I'm going to skip over most of these. There are standard mathematical functions and statistical functions. The binomial coefficient, n choose k, is very frequently used. In how many ways can n objects be arranged k at a time There is the choose command. There is the maximum. It finds the maximum of an array, the minimum, the range. The sum is a common characteristic we talked about. Averaging earlier as noise reduction. Sums and averages, they're equivalent. It's just a constant multiplier in front of the average gives you the sum and vice versa. Quartile functions, so there's lots of these things. Now, one important thing is that oftentimes you're going to have to deal with matrices, okay? In linear models, you're going to see pretty soon, we're gonna do a linear model from scratch, computing the estimates of the effect sizes. But matrix multiplication is different from numerical and vector multiplication. That's why, just remember for now that if you have two matrices and you want to multiply them, you use star, but it needs to be bound on the sides by a percent sign. This means multiply them as matrices. If you skip the percent sign, it would still multiply these component-wise, which is not equivalent to matrix multiplication. Just keep this in the back of your mind. You will get different results, and most likely incorrect results. But R is not going to complain. It says, well, you want to multiply this component-wise, I'll multiply it for you. So, anyways, when you solve it, the solve method is a very efficient representation of matrix inversion, finding the inverses of the matrices, or solving linear equations like this, where this is the coefficient matrix. That's the right-hand side. The question is, what's the solution? Well, run this matrix against the right-hand side, gives you the solution. And there's all kinds of things, row sums, column sums. Okay, here is an NA, okay? R allows you to specify what is the coding for missing values. It could be, for example, a period, dot. It could be NA. It could be a string -999. It could be anything that the machine generates or something. And you see, this is how we would compute the mean. So this is very interesting, okay? Apply the function mean to this data frame, column by column, okay? And go ahead and remove the missing values. NA.rm stands for not available, remove them equals to true, indicates remove these because you can't compute the mean of something that has a missing value. You can say skip over the missing value or impute the missing value, but you can't compute an average of something that has character strings in it. All right, so again, the column B here had a missing value, but you essentially skip it to compute that its mean is 4.75. Let's skip over some of these things. Strings, we can deal with strings. Okay, let me see. All right, there are some examples of simple plotting. We're going to come back to this. Does everybody know the notion of quantile probability plots? So, suppose you have two samples. Sample 1 comes from one hospital and sample 2 comes from another hospital. You want to know, are the distributions of these two samples, if not identical, similar? So in other words, was there a site-specific effect in my measurement? Think about MR scanners. You all deal with, some kind of a digital brain images. People generate phantoms. They literally look like this, except that they're a little bit more mushier and they have a little bit of structure in it. They can put a celery stick in it, they embed it in paraffin. They're literal models, and these travel from one location to the next, and they get scanned so that the scanners get properly aligned to generate similar values. But this is not necessarily guaranteed, and the QQ normal plot allows you to collect a sample from the same population or the same cohort and essentially generate the quantile functions, and the quantile function gives you the first percentile. What's the value of the first percentile? So the value of my measurement, think about some kind of a cognitive score, that gives me the smallest 1% of the data is below, and the 99% of the data are above it. Then the second percentile, 2% to the left, 98 to the right. Third percentile, etc. So that's the quantile function. Imagine doing that quantile function for the two locations, or for the two sets of subjects or something. And then you plot quantile of the first case versus quantile of the second case. And if you get something that looks like this, linear and bisecting the entire space, this means that you have the two distributions are very similar, and you have a good alignment in your scanners. They're calibrated. You know, things are nice when you have linear associations of the quantiles. These are not the values of your function. These are the quantiles, okay? And you see, when you get something like this, it basically says, yeah, except at the tails, these processes are equally distributed. So they're equivalent in distribution, not in values, right? Is everybody kind of with me? So this is an important thing, and the function is very simple. It's just, you know, in this case, we are actually, so X is a normal distribution, 1,000 observations. Y is a non-normal Cauchy distribution. And then you plot the QQ normal plot of X. It basically says, yes, X is normal because it's linear. But look at the QQ normal plot of Y, which was the Cauchy distribution. Nothing to do with a line bisecting. This is called an S shape, which simply means that the Y variable is very, very non-parametric. It has nothing to do with a Gaussian distribution. Very distinct. So you can't use linear models. If these were your residuals, you've got a problem. Too much signal is left in the residuals. Okay? So these are diagnostic plots, essentially. And again, the QQ plot, X versus Y, kind of reports that. Here's another version that kind of shows, you know, very, very non-equivalent things. Low-level plotting commands. Outline does oblique line, just like the line that we saw earlier. Oblique line is a line that's slanted. It's not horizontal or vertical. Yeah? For which one? Up? Okay.
It means that if we have 2 points of data, so if the distribution are the same, we should get a linear.
Yes.
Okay. So if we have one data set and we have some augmentation there, like shifting, rotation, or something like that, so almost similar distribution. We are getting the linear.
Did everybody hear? Okay, so that's a good point. Let's do an experiment right now. The question was, what if one of my axes represents the quantiles for the real data, and the other axis represents the quantiles of a linearly transformed version of the data, right? Is everybody with me? So what does everybody think is going to happen? We're going to do this experiment right now. But do you think it's going to be like this, or is it going to be more like S-shaped like that? So the question is, linear transformations are most of the time preserving of the distribution, you guys. If you take a normal variable and you linearly transform it, it remains normal. So this kind of tells you a little bit that we're not going to see that. We're going to see more of the same. In fact, let's just go ahead and do this real quick. So I'm going to go back to the RStudio, and let's go ahead and grab the settings over here. So I'm going to do several examples for you. The first one, let's call X1 the first series. Oops. Oh gosh. Escape if you want to kill a line. Hold on. Okay. Oh, escape doesn't work here. Oh my gosh, so on a Mac, how do you... Okay, I'm not sure. I think I pressed function escape on a Mac to cancel the line. So what I want to do now is I want to have, suppose x1 is this variable that has, let's just plug in it R normal, and then let's say 1,000 observations. Let's specify the mean to be, let's say 100, and standard deviation of 10. Okay, so let me just do a histogram of this, just to show you what this looks like. Hist of x1, you know, just like you expected. Centered at around 100, the spread is about 10, so you see 65% of the data is between 90 and 110, right? Okay, and then I have, if you aggregate, if you stack all of these things together, they're going to go up to 1,000, right? Because I took 1,000 random observations. So the first question that he asked is, what happens if I linearly transform these variables? So let's go ahead and say y1. Y1 is going to be, let's say, how you want to transform? Let's say minus 13x plus 17. Look, remember x is a vector, you guys, so I'm doing vector arithmetic here. I'm multiplying every element of the vector x by minus 13, and I'm subtracting 17 of the result, right? So let's go ahead and x1, of course. See, it tells me I haven't defined x, I have x1. So I got to up key to get the previous command, and then say x1. Okay, now let's go ahead and do a QQ plot of x1 versus y1. And just like we expected, this is, you know, this is mostly linear, as you can see, it's not a shape. The other thing that I can do is I can do a histogram of y1, just to show you what that looks like. And just like we expected, the histogram shape is not changed, it's the same distribution. Remember, the 17 simply took the distribution and moved it 17 units to the right. The minus 13 took the distribution and stretched it a little bit. It scaled it up. Okay? So, but this doesn't change the distribution. It changes the parameters of the distribution, right? Because they're both normal, except that this one has a huge, in fact, let's just do a summary of y1. Or, I don't know, SD computes the standard deviation. Remember, the standard deviation of the original process, x1, was 10. Oh, and by the way, R is a case-sensitive language. If I do x1 lowercase, it's going to say that I don't know what x1 is. It needs to be capital X1 the way it was defined. So remember, we started with 10, and now look at this. We randomly sampled from this normal distribution, and we requested the standard deviation to be 10. It ended up being slightly higher than 10. Why? Because it's random observations. You randomly sample. So there is no way to guarantee that the sample of 1,000 has exactly standard deviation of 10. There is floating point arithmetic here. Anyways, the second the distribution of the linearly transformed data, however, is huge, 130, right? And it's way shifted off because of the negative multiplier. But if I now take a log, if I take a log of x1 and I call this y2, y2 is log of x1. Now, that's a nonlinear transformation. This is a linear transformation which does not alter the distribution. Taking a log of a variable is everybody knows the log function, right? You guys, very slowly increasing function. In fact, one of the slowest increasing functions with x is defined only for positive arguments. Now if I do the QQ normal plot of these two, it's going to be S-shaped because the distribution of y is known as log normal distribution. It's not Gaussian. It's log of a Gaussian. Make sense? So let's go ahead and do QQ plot of x1 and y2 now. And you see the scales here. See, this is not linear. Does everybody see? Look at the scales, you guys. This is not to scale. This is quite curvy linear indeed. It's not S-shaped, but it's not linear because of the fairly compressed y-axis that we have here. Because remember, log of 100 is 2, but let me just see, x was what? This is the natural log. The base is e in this case.
I think if you change x1 to x2, I mean, the terms, after applying the transformation, I think maybe because they vary.
Oh no, we can make this.
Because the value is, when you are getting log of the small value.
No, the reason why this is compressed, you guys see, this only goes between 4.3 and 4.9. The log function is very slowly increasing, right? So if you go from 100 to 110, it's going to increase very, very little. That's why the y2 variable has such a small, tight between 4 and 5.
Let me just.
Maybe there is a better example.
The thing is, maybe the log is taking just the value, just taking the logarithm of x1, like element y's.
Yeah.
So it's basically just shrinking down the value, but it doesn't really change the distribution shape, isn't it?
It changes the distribution because remember the log. See, this function, the linear function, changes every 2 observations exactly the same, but the log function doesn't because it's not linear. So it changes less as you go along, and it changes rapidly in the beginning and then less. You know what I'm talking about? This function changes the values at exactly the same rate. And I know this is not the best example. We can come up with other examples that kind of give you a more profound, or maybe, let me see, let me just see, how about if I do this? No, this doesn't change this. Yeah, so there could be a better example. I just need to think about that to show the more non-linear behavior of the QQ normal plot. But the important thing is to find out if 2 distributions are the same. Now, in this case, we know that this is normal, this is log normal. They're not the same things. They're totally different. They're related, but not the same things.
X1 is coming from 0 and 1.
No, x1 is coming from it's not 0, 1. It could have been 0, 1, but I on purpose changed it to 110. So the center is at 100, give or take 10. If you do this, you guys, it assumes that x is Gaussian. If you just do this, now it's 0, 1 mean. 0 mean, 1 standard deviation. You don't have to specify them if you're talking about the standard normal. But if you have non-standard normal, you got to specify them.